Hi everyone, and welcome to the 8th episode of the Cancer Researcher podcast, brought to you by the European Association for Cancer Research. In this episode, we are discussing the importance of fundamental, curiosity-driven research for the translational research of the future and for clinical practice. I am your host, Dr. Alexandra Boitor, Scientific Officer at the EACR, and my guests for this episode are Dr. Ruth Palmer, Professor at the University of Gothenburg in Sweden, Dr. Daniel Peeper, Professor at the Netherlands Cancer Institute in the Netherlands, and Dr. Iwona Lugowska, Professor and Clinician at Maria Skłodowska-Curie National Research Institute and Oncology Center in Warsaw, Poland. Hello everyone, and welcome to the EACR podcast, The Cancer Researcher. Hi, Daniel.
Hi, good afternoon.
Ruth.
Nice to see you. Hi.
And hello, Iwona.
Hello, nice to see you.
Today we set to discuss the importance of curiosity-driven research, or blue sky research as it's also referred to sometimes. I think it would be nice to begin our conversation with a few examples of how basic research transformed cancer care. If you'd allow me, I'll open with a classic example that's dear to me, and that would be the development of DNA sequencing techniques, which ended up having a really big impact, I would say, on cancer care at the moment, and most certainly it will have in the future. The genome from cancer cells is routinely sequenced in many hospitals at the moment in order to aid oncologists in treatment decision. And lately, there's even a push from ambitious research consortiums, such as CGI Clinics, for instance, towards whole genome sequencing of cancer cells to further improve cancer treatment decisions and find the role of variants that today are of unknown significance. So here we can actually go back to the development of the DNA sequencing technique by Sanger in 1977, or the development of PCR by Kerry Mullis, both of which won Nobel Prizes for their contributions. But we can go even beyond that and think about the discovery of DNA polymerases in the late 1960s, when Thomas Brock, a microbiologist from Cleveland, and his undergraduate student conducted research in Yellowstone National Park. And driven by the simple curiosity of finding out what forms of life could live in spring waters at temperatures above 70 Celsius degrees, they discovered Thermos aquaticus, the organism that had the DNA polymerase that we routinely use nowadays. And anyone at that point couldn't have predicted where this was going to go. Do you have any examples that you want to share?
Well, absolutely. I think that's a great example, and there's so many of them. For me, one that's dear to my heart, I guess, would be the discovery of tyrosine phosphorylation, which really came on the back of studying viruses and infection. Viruses, of course, that drove tumor development, but that led to the kind of accidental, I guess, discovery of tyrosine phosphorylation and the understanding that there existed tyrosine kinases, and later on our understanding that many of those drove oncogenic processes. And on the back of that, I guess we can say that there's been very many tyrosine kinase inhibitors which have been developed, and many which are used in the clinic today. And I guess the one that most people think about is imatinib, which is used in CML and really has changed the landscape of that cancer and its treatment. So many wonderful examples. For me, that's one that springs to mind, of course.
Yes, Alexandra, you mentioned already the introduction of DNA sequencing techniques, and I think those kinds of technological advancements have been really instrumental shaping the field. So one of the other positive consequences of the introduction of sequencing is the discovery of the BRAF gene with a mutation that is common in human melanomas and several other cancers around the early 2000s. And now we see that it has led to the development of very specific inhibitors targeting BRAF or its downstream kinase in the pathway, MEK, and melanoma patients receive a decent benefit from the treatment with those inhibitors. And this was only possible thanks to very fundamental research that led to the identification of the BRAF oncogene. But my favorite example, I guess, is the introduction of immunotherapy, which is resting on the shoulders of thousands of immunologists who have been working literally for decades without very clear prospect, one day using that knowledge and translating it into benefit for patients. And, many of those immunologists did not really have the direct goal of our idea how we can develop cancer immunotherapy. And the rest is history. Nobel Prizes have been awarded for major discoveries that were only possible because of many decades of very hard fundamental research that led to a better understanding of how immune cells respond to antigens, how they kill, how they are inhibited, and how we could translate that clinically by using that understanding and shaping very clever therapy to reinvigorate those immune cells to fight cancer. So there's many, many more examples, but I think these are close to my heart and also worked on in my lab because we still have some problems to solve.
I can say also it's close to my heart because I deal with melanoma patients, and BRAF and immunotherapies are extremely potent and breakthrough technologies. However, answering on your question, I don't want to say anything about technologies. I would like to tell about Maria Skłodowska-Curie, because she's also a Nobel Prize. And I really think that this person shows how to give a breakthrough work in a field in medicine, especially in radioactivity, and aim to transfer this knowledge directly to implementation into clinical practice and the benefits for societies. Also very important in terms of Skłodowska, that's at her medical application, cancer research, and everything what it was related to radiobiology. It's one, and a second is a collaboration, humanitarian goals, education and research, as well as inspiration for future generation. So with this, I think we can move forward in terms of how to do the research from preclinical to clinic. Thank you.
Wonderfully said. I think it's quite obvious that this is hardly a new subject, quite the opposite, as the scientific community has continuously stressed the importance of basic research over the past few years. For instance, Science published a paper about the role of fundamental research in medicine in 2018, and more recently, there was a Nature paper, I think, at the end of last year, stressing the importance of purely curiosity-driven research with no clear idea of its potential impact. The European University Association annual conference in 2021, so at this conference, the president of the association, Professor Michael Murphy from University College Cork, said, and I quote, "We've got to take a good look at whether the balance is right between mission-driven research and investigator or academic-initiated blue skies thinking. That balance may be going out of kilter." So what do you think? Is there enough fundamental research at the moment to sustain the translational research of the future?
Yeah, if I may take this first, I think there's increasing pressure from funding agencies to focus on research that they say would be quickly translated into the benefit of the patient. And I think there's two very important elements to this important discussion. On the one hand, it is true that, like never before, the gap between basic research and clinic and pharma as a third party has been reduced. So the different areas have become closer together, and that offers possibilities like never before to translate findings from basic research to the clinic, and we should definitely take advantage of it. But there's also another side to the story, and that is that of all the wonderful examples that we've just mentioned, and there are many, many more, I think the point is very clear that the pipeline needs to be filled, and that is possible only if we keep investing a lot of our resources in pre-fundamental research where the obvious benefit for the patient is not clear, but we've discussed already several examples how such ideas in the end were very fruitful, could be translated, and are being used in a daily practice in the clinic for diagnosis and for treatment. So I think we should keep our eyes open both to translate whatever we can from basic research, but also make sure that we keep filling the pipeline by giving researchers all the space that they need to make breakthrough discoveries.
I think that one of the things is that in the last 10 years, I think the landscape of science has fundamentally changed in a way. So we've really moved quite a lot from, asking smaller hypothetical driven questions to the age of big data. And I find that we're almost in a kind of a crisis where, we don't really know how to put these two things together in a very happy marriage, because the potential is there to do so many things. But we need to remember the skill of validating in a very careful way so that we stand on very solid foundations in terms of the really important findings that we would like to take further into the clinic. So, and I think that having this balance is very difficult. And I think at least in many countries, the push is quite politically driven for translational research. But we need to remember that it's been pointed out already that all of this needs to be built on very strong foundations. And I think there's no way around this hard work that needs to be done to make sure that the basics are correct, because everything that is done in big data really depends on information that goes in, right? And this is also critical. So I think we're in a sort of a flux where we're trying to adapt in a way. The scientific community is trying to adapt so that we can maintain fundamental research, but we can also capitalize on the technology and the opportunities that there are. So at least I feel that we're in this kind of period here where everybody needs to think a little bit differently, but also to preserve the very important hypothesis-driven, curiosity-driven research that really needs to continue.
So I can only add that as a clinician, it's always very important for me to have the collaboration with my colleagues from preclinical and basic research departments, because then we can have the kind of evaluation from, let's say, mission or curiosity-driven ideas into practice, and then with feedback where we are. So the reward evidence is one of the key aspects, because then we can evaluate what's going on in clinical practice and with our innovation. I would like to also stress a little bit that during COVID pandemic, we noticed that we can do a lot and limit all those burdens related to bureaucracy and move significantly forward into our goals, because the stress was huge. So I think the concentration on research, not anything which is not that much benefit, by reducing bureaucracy and all these legal aspects, or at least finding simple solution, it's something I'm looking for very much.
And on that note, maybe not strictly bureaucracy, but in terms of paperwork in a way, like, for instance, when you apply for grants, so grant applications often ask to state and demonstrate the impact of your research in order to be funded. And I was wondering, how does that square with not knowing how it will develop?
Oh, there's definitely tension there. I'm not a big fan of asking fundamental researchers to predict how their findings would translate in 3 or 4 years in major changes or improvements in clinical care. We're talking about fundamental research. We should give enough space to make breakthrough discoveries. And then you make these beautiful findings like discovering a heat-resistant polymerase, or a target for immunotherapy, or a target for tumor precision medicine. If you would not give that space, you would probably not give enough funding to make these breakthrough discoveries. So I think we should move away from requiring investigators to predict how their findings will benefit the society or the patient. We may speculate if all this research will be successful, then I could envisage that this and this would happen. That would probably be fine, but making funding dependent on the outcome predicted by the researcher, I think, is a very dangerous game.
So I don't by any means want to dispute or undermine the importance of translational and clinical discoveries, but I was wondering whether current big grant calls allow for this sort of research, or are they, in your opinion, too prescriptive about solving a particular problem?
I would, if I could say something, I would say that the ERC grant funding is particularly free from that. Among many of them. But I would say in the landscape here in Scandinavia, also in the EU, then of course it can be very heavily translation driven at the moment. I think that's most people's viewpoint, but slight concern as well that it's become a little bit too much. But the ERC has managed to maintain, I think, a more hypothesis driven scientific funding policy. And I think that's important, actually.
I'm involved in UNCAN projects, and this is initiative of the European Commission. And this is a preparatory project to first assess current knowledge and needs, and then to set the clear goals and priorities to wisely allocate resources. So this is the right approach, because we cannot solve all problems. However, to do it wisely and to allow collaboration and the transfers from preclinical, from basic into clinics, it makes sense, as I mentioned, in collaboration and appropriate relocation resources. And of course, this impact is always the question when I'm struggling with writing a grant proposal. What I can write here? I just need to write something. However, the research can show completely different stories, and we can also explore completely different fields at the end, even more valuable.
I think that the ERC funding scheme is indeed an excellent example where investigators have full space to come up with breakthrough ideas without the pressure to have a very strong translational outlook. If it's there, one should definitely use it, but it's not a primary requirement to receive funding. And to your question, I think that also the CUK grant challenges speak to this. They do allow for very fundamental research to take place. And if there is a finding that allows clinical or preclinical translation, then they will also be funding those opportunities. So they cover both of the two elements that I mentioned earlier, which I think is very important. And I would hope that many other agencies would follow those important examples.
On that note, are other grant calls dedicated to fundamental research, and are they matching the funds for translational research?
That's not the case. So I think increasing. So part of my lab works on Drosophila, and I have many colleagues that only really work on Drosophila. I would say that that's for example, one of the model organisms, along with C. elegans, that's contributed fundamental understanding to signaling pathways that are been very important to understand tumor signaling. And however, they find themselves, I think, many of them in a position where they have no direct relevance to looking at fundamental processes and unraveling fundamental developmental signaling pathways. And this is quite difficult to fund at the moment. I think across Europe, it's becoming a little bit out of fashion to work on in such niche areas when you don't have the other half of your lab, as I do, working on, mouse and cell pathways. So I think this is really problematic, because we need to make sure we bring these very important model organisms and also the skill sets in those scientific communities, which are really important. And we don't want to lose them either. So, but those labs, they tend to have much smaller budgets. That's because the resources they can apply for are smaller, and they generally tend to not be able to go for more translational grants. They find themselves shrinking, and a lot of people have moved out of that area. So I think we have to be careful about our funding, and this is a discussion which is very active, at least in Scandinavia. But this is what we're also talking about today, that if we don't maintain these kind of scientific communities, then it's difficult to build them back up again.
I echo this. There's one discovery that we haven't discussed yet, but that is CRISPR-Cas9, and this came from investigators studying how bacteria defend themselves against viruses. This is not typically research that would be funded today by Cancer Society, or perhaps even at all. But I think there's very few cancer labs in the world that are not using CRISPR-Cas9 on a daily basis. It has truly revolutionized our work. And I think that's yet another example that illustrates how important it is to keep funding free and open fundamental research, not just for cancer treatment, but perhaps beyond that, much more general. And again, once we have an opportunity to translate discoveries, we should certainly do this. And we have many opportunities nowadays, because the gap with pharma and the clinic is much smaller than it was 10, 20 years ago. And indeed, like, at the Netherlands Cancer Institute, from time to time, we do make breakthrough discoveries in fundamental research lab, which will translate in an investigator-initiated clinical trial. So there are many examples of that translation.
As we've discussed, the history of science clearly shows that curiosity-driven basic research is a prerequisite for applied research. To come full circle and close our conversation, what do you think is the biggest risk that would come from neglecting funding for basic research?
I think it's quite easy that the pipeline will be dry. So we will be able to translate the current findings for the next 5 or 10 years. But then there's nothing to be translated any longer because we forgot to make breakthrough discoveries. So we need to keep filling the pipeline by fundamental research.
Fundamental research for me is the first step. If we do not, the first step, it's not possible to move further.
I can't add much more than that. I really think that the value of unexpected discoveries in any lab, anywhere, at any time can't be underestimated. So I think the element of surprise will be reduced, and that's really, really important to keep.
Thank you very much. I would like to end this episode with some food for thought. So I'll leave you with a quote from Professor Daniel Peeper's presentation on the topic that we debated here today. Ultimately, scientific discoveries are not made in the lab, they are made in the brain of the scientist.
I don't necessarily agree with that. We imagine what will happen, but it is the breakthrough discoveries that we couldn't imagine, which are very important. We could not imagine that CRISPR enzymes or CRISPR-Cas9 enzyme in the bacteria would protect the bacteria against virus. It was a discovery which was unanticipated.
Yeah, I think that is really true. It's these wild cards, right? Who knows where these wild cards are coming from? If I knew, then I would be after them straight away. But that's the problem. We don't know. And I think they can come from anywhere. And that's part of the true excitement of science. When you go somewhere and something pops up that's completely wild. And then in the next 6 months or so on, 2 years, it unravels the enormous potential this has. And this happens all over the place, but it's unpredictable. It's super unpredictable. It's like, where are you going to find the next tennis prodigy or the next, where are they? The next maths prodigy? You have no idea. They're popping up somewhere. And if you don't keep looking for it and supporting it, then you don't have them, right? So.
Yeah, I think these statements are very important. Also what Ruth mentioned, that it adds to the excitement. This is why we're doing this job, to make a discovery that nobody else had expected. Not that we made it, but that this could be possible, right? That you made that particular discovery. Mm-hmm. That should also attract the young people to come to the lab and do exciting basic research, to make true discoveries that you cannot forecast or predict.
I absolutely agree with you, Daniel. I can even take it further, because I think that you can't do research properly if you don't burn for it. And from the very beginning, when you're a baby PhD student, the first things you find, they're amazing to you, right? These are maybe not Nobel Prize winning discoveries, but they are huge in your own place, right? And then you build on them. This is what makes you work and be interested and look at this and dig into this tiny little problem that really few people in the world care about. And somewhere in all of that effort, there comes these amazing discoveries. And this is what we live for, right? So it's so driven by curiosity and interest that I have a hard time to think you can actually organize that kind of drive. I think, you start organizing it all and it's all going to be then you will lose this flashes of, what's human about science in a way, right?
Yes, the unpredictability is so super exciting.
Yeah.
The few discoveries that I've made as a PhD student and in a postdoc, I still remember them because they were unexpected. I didn't think that this could happen or would happen. So the unexpected element of those discoveries is key. And that's why we should create as much space as possible.
We can only keep fingers crossed for new generation to have the such enthusiasm in terms of research that we've got.
Well, yes.
Absolutely.
Thank you very much for this lively conversation. And thank you for being my guest today. I really, really enjoyed chatting with you.
My pleasure.
Thank you.
Thank you. Nice to see you guys.
Thank you.
Likewise. Bye-bye.
Take care.
Bye-bye. Thank you.
Bye. We really hope that you enjoyed listening to Ruth, Daniel's, and Iwona's conversation on the importance of fundamental, curiosity-driven research. I hope you found interesting and helpful the examples and opinions they shared, rooted in their vast experiences. I would like to once again thank our guests for being here with me today, and many thanks to everyone who listened. Please subscribe to our podcast so you wouldn't miss an episode. You can find The Cancer Researcher on your podcast platform of choice. We're on Spotify, Audible, Apple, Amazon, and Google Podcasts. Please do us a favor, subscribe to our podcast, and tell your friends about it. You can give us feedback or offer suggestions for other topics or preferred guests through our feedback form that you can find on our website at www.eacr.org/podcast. That's www.eacr.org/podcast. And don't forget that you can also find us on the platform formerly known as Twitter at EACR News. We're also on Instagram at Hello EACR, and you can search for us on Facebook and LinkedIn. We will be taking a short winter break, but I can assure you we are working on new and exciting content. We'll meet you in the new year with a brand new season of the Cancer Researcher podcast. Until then, happy holidays everyone!